Hello, everyone, and thank you for your attention. My name is Charles Neal, and I'm a research scientist here at Google. And today I'm going to be talking about a recent paper of ours entitled Accurately Computing Electronic Properties of a Quantum Ring. If you'd like a link to the paper, you can just scan the QR code on your screen. So let me begin by motivating the kind of work that we're doing here by talking about spectroscopy and how spectroscopy provides a generic quantum metrology tool with two key features. It's robust to experimental imperfections, and it's extremely accurate. So let me go over an example here, which is the emission spectrum of helium. Right, so how do they run this experiment? They take a tube of helium gas, they take a laser, they shine it at the tube, and they look at how much light gets reflected off, and they record that with a camera. Now, there's all sorts of things that might go wrong in that experiment that would make it not quite perfect. So perhaps they don't know the exact intensity of the laser light, perhaps their detector has some finite efficiency, and all of these are going to lead to some unknown amplitude to these peaks that's hard to control in a real experiment. And often that's why you'll see these things plotted with arbitrary units on the y-axis. However, if you go to any one of these peaks, what you really care about if you want to, say, learn about the atomic structure of helium, you care about the exact frequency at which these peaks occur. And you'll notice that these peaks are extremely narrow. And the more narrow they are, the more accurately you can learn about the quantum system that you're trying to study. So in that sense, spectroscopy is robust in the sense that it doesn't care about all these experimental imperfections in the amplitudes. And it's accurate in the sense that you can get extremely narrow peaks, which gives you very accurate information about the frequency of the transitions in the atomic system. So in this talk, what we're going to do is we're going to apply these generic notions of spectroscopy to accurately compute properties of a large multi-qubit system. So let's look at the qubit connectivity and the circuit diagram that's going to apply to all of the data that I'm going to show today. So on the left, what you're looking at here is a cartoon of the Sycamore quantum processor. It has 54 qubits, and what we've done is we've taken 18 of the qubits, and we're going to use those for this experiment. So the qubits are shown as pluses, and the couplers between qubits are shown as blue squares. So what we're going to do is we're going to start the experiment by taking one of the qubits, and it doesn't matter which qubit we use. We'll take one of them, and we'll put it into the plus x state. And then we're going to apply some evolution. This evolution consists of single qubit z rotations and square root of I swap gates between pairs of qubits. So within a cycle, we're going to apply both a layer of square root of I swap gates to half the pairs simultaneously, and then to the other half of the pairs in the next moment. And what this does is it allows within a cycle for all of the qubits to couple to their neighbors, and after one cycle, you end up with some generic entangled state. And then what we do is we apply this cycle of evolution over and over and over again many times. And at the end of the circuit, what we do is we measure one of the qubits and we perform state tomography. So there are two key aspects of the qubit connectivity and of this circuit that I really want to emphasize. First of which is the connectivity is periodic in space. As a result of this symmetry, you naturally are going to get conservation laws associated with the symmetry. In this case, it's going to be momentum. So because it's periodic in space, we know that we're going to have eigenstates that act as plane waves, and these plane waves are going to have definite momentum. In addition to this, the fact that it's periodic in time means that we're going to have a well-defined notion of energy and energy eigenvalues. So what we can do is we can treat this ring of 18 qubits as essentially a condensed matter system, like a one-dimensional wire, with eigenstates with well-defined energy and momentum. And we can actually use these intuitive condensed matter physics notions to characterize our large multi-qubit system and understand its performance. And that's what I'm going to be talking about in the rest of my talk. So let's get to the data. So here we're going to look at how we can measure the single particle energy spectrum of our effective one-dimensional wire. So as I said before, I take one of the qubits and I perform state tomography, and this allows me to measure, say, the expectation value of sigma x and sigma y on that qubit. And what I can do is I can plot those expectation values as a function of the number of times I repeat the cyclic evolution. And what you see is, you see some wiggles and they're not particularly intuitive. I can't really pull out any meaning from the raw data. But if you simply construct the quantity x plus iy, and this is somewhat of a special quantity, and you just take a Fourier transform of x plus iy, what you see are very clear, very well-resolved sharp peaks. And what that means is that we're actually extracting the energy spectrum of our effective one-dimensional wire, and we're just plotting the Fourier amplitude as a function of the Fourier frequency, and we see 10 peaks. So what we can do is we can go to each one of these peaks and just label it by its index. And on general grounds, we know that this index is associated with the momentum of each eigenstate, just by those symmetries that I mentioned earlier. So now what we can do is we can take the center frequency of each peak and plot it on the y-axis. and the index of each peak and plot on the x-axis. And what we're effectively constructing is a diagram of energy as a function of momentum, which in condensed matter physics is known as a band structure. So again, each blue dot is just the observed peak position in the experiment. And what I'm plotting here is 1,000 sigma error bars. So had I plotted 1 sigma or 5 sigma error bars like you kind of typically do, you wouldn't be able to see them. They'd be so small. So what I'm doing is I'm plotting 1,000 sigma error bars because the uncertainty in each one of these peak positions is at the 10 to the minus 4 radian level, which is extremely accurate for a multi-qubit experiment. In addition, I can plot the ideal band structure as a black line. And what I can do is I can look at the difference between the data and the ideal. This is kind of a metric of how well our system is performing. And you can see that we can accurately get the peak position at the level of 0.01 radians. So for a large 18 qubit experiment with very large depth, these are quite amazing results. So what I'm showing here is that we can accurately and precisely resolve these peaks using momentum resolved spectroscopy in an 18 qubit experiment. So let's take this condensed matter analog a little bit farther, right? We have a loop, it acts as a wire, and we can produce a synthetic flux which threads the loop. What happens now is when particles go around the loop, they accumulate a complex phase, known as kind of an Aharonov-Bohm phase, and this is associated with the magnetic flux. So if you just add up all the phases, that acts as a flux. So what we want to do now is we want to ask, how do these energy levels, just peaks in our spectrum, depend on the external flux that we're applying? Again, it's a synthetic flux. And we're going to consider two cases. We're going to consider the case with just the native disorder. This is disorder due to small errors in our unitary parameters that we're applying. Maybe there's small miscalibrations or something. And those introduce disorder in the system. And what you see is the data is in blue, the ideal spectrum is in black. And what you see is very good agreement. And at zero flux, you get this degeneracy of the levels. Essentially what's happening is, in the absence of flux, plane waves traveling clockwise and counterclockwise have the same energy, making them degenerate. And then as you apply the flux, what this does is it breaks that degeneracy and it increases the level spacing between neighboring levels. The other thing we can do is we can synthetically add disorder beyond what shows up natively. And that's what I'm doing here on the right. And you can see that the effect of disorder is actually to introduce gaps in the spectrum at zero flux. And what you can show and what we show in the paper is that each one of these gaps is exactly related to the spatial Fourier amplitudes of the exact disorder pattern that we're seeing in the system. And what this means is by taking these plots and measuring these types of curves, what you can do is you can actually diagnose the exact disorder pattern in your 2 qubit gates by simply looking at gaps in the spectrum. So we can take this again to the next step, right? If we have disorder in our system, it makes you think of, you're going to get things like finite conductance and scattering. Again, just drawing on these condensed matter analogs. And that's what we're going to look at here. We're going to look at how we can infer current and conductance from these avoided level crossings. And we're going to do this as a function of the disorder that we add into the system. So let's look at the first plot. What we're doing here is we're looking at energy as a function of flux, just as we were doing in the last figure, but I'm now zooming in onto just 2 of the levels to get a very clear picture of what's happening. And then the data is in the circles. And what you can do is you can fit this to a very generic model. This is just a square root of x squared plus y squared. And this is just what shows up whenever you get close to an avoided level crossing in a spectrum. And you can fit this. And then what you can do is you can take the derivative of that with respect to flux. And this one can show is equivalent to current. And again, you can look at current as a function of flux, and you can see very intuitive features. You have regimes that are dominated by disorder, you have clean regimes, you have intuitive physical notions like persistent current. And then what you can do is, again, just take another derivative, second derivative of energy with respect to flux. And this gives you a well-defined notion of conductance. And this is known as Tallis conductance. And what we're doing here is, we repeat this experiment, we construct conductance, and we do this as a function of, how much disorder did we add to the system? And again, these are, site-to-site variations in our 2 qubit gate parameters. And what you see is that as we increase the disorder, you see a strong suppression in the effective conductance with increasing disorder strength, just as you'd expect in a standard condensed matter system. And if you compare the data, which is the dots to the ideal value, again, you can see very accurate agreement between the experiment and the ideal behavior, which again, in the context of an 18 qubit experiment with over 1,000 2 qubit gates, I think this is quite an amazing demonstration. So again, we can use these intuitive notions of current and conductance and actually use it to quantify the system performance at scale. And with that, I thank you for your time, and I leave you with our team that made all of this possible.